So we're going to continue our discussion of the terrestrial planets, and last time we discussed Mercury as it stood as a planet which was the closest to the Sun. Next we're moving outwards to Venus, and this is basically contained within chapter 7 of your book, and we're going to discuss Venus pretty much in terms of the Earth and compare the Earth and Venus together. So as usual, Venus was observed for thousands of years before astronomy was turned into a science. And we know about the famous depiction of Venus. So here's Venus. Sadly, her arms are missing, the famous statue, which I believe is now in France. Not an art expert. Venus was also incredibly important to the Babylonians, and the ancient Babylonians referred to Venus as the goddess Ishtar, and basically Venus was a love goddess, and that thinking came down from the Babylonian idea, where Ishtar was a goddess of love and fertility and various things like that. So this is a sample of what's known as the Ishtar Gate, which is located in modern-day Iraq. And this was basically a gate which was decorated to this goddess and actually depicted a number of images of the planet Venus itself. Ishtar, as it happens, was also an awful film that had Dustin Hoffman and Warren Beatty in it. So let's get on to Venus the planet. So Venus as we know it now has a radius of about 6,000 kilometers, and that is about 5% smaller than Earth. So if the Earth radius was 1, Venus would be about 0.95 Earth radii. So it's very close in size to that of the Earth. Its atmospheric pressure is incredibly high. Earth has an atmospheric pressure of about 1 bar. The atmospheric pressure in Venus is 92 bar. And we're going to discuss some of the effects that that has on the planet. But that is an enormous atmospheric pressure, and Venus has some of the most extreme weather in the solar system. Its year is 225 Earth days long. Its day is 243 Earth days. It has a retrograde rotation, meaning it spins the opposite way on its axis to the Earth, although it goes the same way around the Sun. Its density, it's close in density to Earth. It's the third most dense object in terms of the terrestrial planets behind Earth and Mercury. You never actually see the surface of Venus. Any observations of the surface of Venus have been done at radio wavelengths. At visual or infrared wavelengths, the atmosphere is so thick that you can't actually see the surface, and the surface of the planet is completely obscured by cloud cover. It's also the closest planet to Earth. Mars has been explored a lot, and you always see a lot of fiction and a lot of discussion of the planet Mars that we will come to. But in terms of being our closest neighbour, Venus is it, at 42 million kilometres in orbital distance from the Earth. So there's a comparison of Earth and Venus. In terms of Earth, you can see there are white fluffy clouds with gaps in so you can see through to the surface and radiation can penetrate, and you have a lot of water on the Earth. The chief feature on Earth that is missing on nearly every other planet is the presence of liquid water. Now I say liquid water because some places have a lot of water ice. And here's the surface: rocky terrain, icy terrain, and we have some volcanic features. And here's some water. Venus, well, it's pretty much all rock. This image here is taken through the atmosphere using radar observations. So if we strip away the atmosphere and have a look at the surface, Venus is really just a rocky ball that has been mutilated and generally formed by volcanoes. The morphology that we find is predominantly volcanic, and there's a lot of volcanic activity on this planet. So let's put the atmosphere back on, and what do we see? Well, if you look through a telescope at Venus at any time, all you'll see is a very bright disk. You may see a phase, as we discussed previously in terms of Galileo's work, but you will really see a bright disk. And the reason being that Venus has a lot of carbon dioxide cloud. Now this is something to consider when we talk about Mars. Mars also has a 95% carbon dioxide atmosphere. But what you've got to remember at Mars is it has a very low atmospheric pressure. Venus has a very high one. So you can't really compare the two. So Venus in the night sky is an extremely bright object, and it is visible at the moment just before sunset. And it gets to a magnitude of about -4.6, and that's actually an extremely high magnitude. We'll talk about magnitudes a little more later. We've already discussed them previously in the capacity of stars. It's completely shrouded by high albedo CO2 cloud, so it's reflecting a lot of light, and its albedo is almost 0.76. That means it's reflecting 76% of the light that's hitting it. The rest of it is being absorbed. And that makes it very bright in the sky, hence its importance to a lot of the ancient peoples who named it after their god. And in this particular image, this is Venus. If you go outside and look for this object, you'll notice it because it appears a little larger than other objects. Once you start to recognize planets in the sky, you always wonder why you couldn't see them before, because you can actually see the curvature. They look different to stars. Locate it for yourself, or if you need a hand or any guides of finding it, please contact me and I'll help you out. But try and find some of the planets as we discuss them in the sky and compare them to stars, because you'll always recognize them forevermore afterwards. So we were discussing the atmosphere of Venus. So we're looking at about 97% carbon dioxide, 96.5%. Now remember, carbon dioxide is easy for smaller planets to hold on to due to its relative weight. We're also looking at 3.5% nitrogen and then traces of everything else. Sulfur dioxide through neon being relatively popular compared to some of the other sulfides, chlorides and fluorides. Now, this percentage of sulfur dioxide is rather important because there's actually sulfuric acid rain on this planet. The sulfuric dioxide content is obviously higher here than water vapor. 0.015 for sulfur dioxide, 0.02 for water vapor. So not much water in the atmosphere of Venus, whereas there's a lot of water in the atmosphere of the Earth. Whereas sulfur dioxide, 0.15. So you're more likely to get sulfur precipitation than you are water precipitation. So Venus's atmosphere, like we said, 96% carbon dioxide, 3.5% nitrogen, not much water, hydrogen sulfides, hydrogen chlorides, hydrogen fluorides. And because of this unique chemistry, you end up with a system of thick clouds of sulfuric acid and lots of sulfur crystals forming in the atmosphere. And that will precipitate out as rain does on the Earth. So as water falls from the sky on the Earth, sulfuric acid will pour from the sky if you're on Venus. So we complain about acid rain on the Earth, but it's really nothing like that you get on Venus. And if you look at the rocky landscape of Venus shown here, not only is the rocky landscape actually influenced by the terrestrial volcanoes spewing lava out onto them, it's also heavily influenced by the fact that sulfuric acid is constantly falling onto it and mixing these rocks and weathering these rocks down. So there's a big effect of the atmosphere on the surface here. And when we're talking about life in the universe, it would be very difficult to have life on this planet. If you imagine anything like human life, it really wouldn't take well to being rained on by incredibly intense sulfuric acid. There is another thing to consider. Carbon dioxide and the content of carbon dioxide gas in Earth's atmosphere is a big point of contention right now, with people trying to curb emissions and online companies trying to send you emails to rip you off in buying carbon offsets and all sorts of weird things. But the greenhouse effect is a real thing. And if you look at it in terms of Venus, it's a very, very extreme thing. You're talking 92 bar atmospheric pressure, so you're packing a lot of gas into a small space, and most of it, in fact 96% of it, is carbon dioxide. Now when the carbon dioxide is surrounding this planet, radiation passes through it and then is trapped inside. So the temperatures on Venus are actually 470 Celsius both day and by night. So we're looking at temperatures hotter than Mercury, a planet that's actually closer to the Sun. So the equivalent pressure on Earth, if you were attempting to look for a point on Earth that had the same pressure as Venus, would be about 1 kilometer under the ocean. A place where the majority of our vehicles that we can actually create, submarines, things like that, ROVs, tend to just completely implode under the pressure unless they're really bolstered. So there's a very high CO2 atmosphere, and that allows heat to actually enter but doesn't allow it to leave, because the radiation penetrates through the cloud and then hits the surface of the planet, is absorbed by the surface, and as we discussed before when we're talking about black bodies, the rocks will behave as a black body and they will re-radiate the radiation at infrared wavelengths. The CO2 clouds then trap the heat and cause a feedback loop which gets the planet hotter and hotter and hotter, and the temperatures continue to increase until they reach an actual saturation point of which they cannot get any hotter. And there's sort of a low resolution image, but still a good image, that shows this. The sun's rays can pass through the carbon dioxide cloud layers, hit the surface, warm up the surface, and then those rocks radiate heat which gets trapped by these cloud layers. And then that heat really bounces around between the surface and between the cloud layers and keeps the planet at the same toasty, in excess of 400 degree temperatures all the time, day and night. So here's an image of Venus's clouds. As we mentioned before, it's got some odd rotation, very slow daily rotation, so you don't end up with the dynamic weather you do on Earth. You end up with sort of latitudinal cloud belts around the equator, and then lighter areas. These lighter areas are probably the sulfur dioxide clouds we discussed. Mariner 10 image of Venus, pretty much the same. And there's another picture of Venus with some cloud. So we're looking at these in the visual. What happens if we switch to the ultraviolet and take a look at Venus? Oh look, it still looks like cloud. This is actually from a Hubble Space Telescope image of Venus, and this is done in the ultraviolet part of the spectrum, and you still don't see much more than you saw in the visual. So it's a little bit difficult to observe Venus. So one of the unusual things about Venus is that it rotates backwards. It has that retrograde motion we discussed. One of the reasons is it could have been set backwards by an off-center collision with some planetesimal. It has a molten core, it's got a dense atmosphere, and it's rotationally it's being gradually reversed by various solar tides in the atmosphere. It could also have been due to the direction of the angular momentum in the solar nebula. Now, I don't think the molten core and the dense atmosphere rotation theory is technically true. That would take a lot of energy to actually reverse the rotation of a planet. So I would tend to discount this, but some people still do believe this may be true. I think that either this option or maybe this option are true in these cases. Likely option 3 in my opinion. But whatever caused Venus to rotate in the opposite direction to the Earth is somewhat problematic, because Venus's atmosphere is actually rotating in the opposite direction to the planet. In which case, I revised my idea a little bit This could be a little bit true, but still, it's an open question. No one's really sure quite why this is the case, but we do have this observation that Venus is a planet, rotates one direction, its atmosphere goes in the opposite way. So in terms of its atmosphere, its highest cloud layer is about 68 kilometers above the surface, and then it has various layers below. You don't need to memorize these are just for your information. But about 33 kilometers, you get a thin haze, and below that the air is clear. So if you could stand on the surface, you would see through the air, and you would see these clouds hanging above you. And there's various observations of the winds on Venus, and what we're seeing here is 300 mile per hour winds in the upper atmosphere. And the atmosphere of Venus has actually been explored very, very well. And Venus was the only planet so far in the solar system into which hot air balloons have been deployed to actually survey the atmosphere other than the Earth. So the Vega 1 and Vega 2 probes sent by what was then the USSR dropped balloons into the atmosphere, and those balloons survived for almost 2 days and were carried about a third of the way around Venus by those really high-speed winds we were discussing. And it's found that the slow rotation of Venus affects the winds. It doesn't break up these huge circulation patterns like we get on Earth. On Earth we have a big influence of the rotation of the planet on the atmospheric energy budget and the way that the air is circulated. That doesn't happen on Venus, so you end up with really high winds. We also found out that the upper atmosphere is relatively cool and the lower atmosphere is relatively hot, 745 Kelvin, though not as hot as the surface. And here's a picture of the Venus balloon, the very sort that was dropped. So there's long party balloon shape with a system of weather observation packages hanging beneath it. And we found out that the present atmosphere is extremely dry, that it probably had a lot of water in it in the distant past, based on looking at water isotope abundances like deuterium. The water was broken up by ultraviolet radiation, and hydrogen was probably lost to space. So UV radiation went into Venus's atmosphere, broke up the water molecules through hydrolysis, and lost the hydrogen and the oxygen, went their separate ways, and the hydrogen boiled off into space. It was pretty much too warm for water to fall as rain and only form any oceans, and then the greenhouse effect kept any other oceans on forming, and if there was any water oceans on Venus, the greenhouse effect would have dried them all up. And that's because, as we said before, carbon dioxide is transparent to light, but doesn't let infrared radiation out. So light gets in, heat doesn't get out. So Venus's atmosphere, being 96% CO2, gave a serious effect and trapped heat. Earth's is about 0.03% CO2. So you can see the contrast between the two planets there. Earth's oceans are actually extremely useful, and they actually absorb a lot of carbon dioxide, and that diminishes our greenhouse effect, and that also has an effect on the acidity of the oceans. So there's possibilities that earlier in Venus's life, that when it was young it may have been cooler. It did form 30% closer to the Sun than the Earth did. As it didn't have any liquid oceans survive, there was nothing to absorb the CO2. Volcanoes also poured out CO2, and the water vapor was destroyed, and the CO2 stuck in the atmosphere. And all the sulfuric compounds were also likely vented by volcanoes. So, that's really the atmosphere. The surface of Venus, well, we can't see it. We had to take probes to Venus that actually had radar on board, and those radar-capable probes bounced radio signals through the clouds and off of the surface and returned us an image. We got altitude and surface characteristic detail. Was it a rough surface, a smooth surface? and built images that way. So any image you see of the surface of Venus is false color and is just based on radio data only. So the IAU, which means International Astronomical Union, as we discussed with constellations, they decide on all the names of celestial bodies such as planets and the features on them. All features on Venus, with Venus being a female deity, all their features have female names. There's only a couple of exceptions. The Maxwell Mountains, Alpha region, and Beta region are the only exceptions. But the highland regions are called Ishtar Terra, and we have Aphrodite Terra, both, again, goddesses of love that were used to name these two regions. And both female deities, of course, being goddesses. So in terms of volcanism on Venus, shield volcanoes, very much like the Hawaiian mountain range, are the dominant surface features. And these are really formed by fluid lava that form over a hot spot on the surface and flow out and create these low-profile volcanic peaks. And then they erupt and they erupt and they erupt, and they produce a volcano with tons of layers on it. So these volcanoes aren't formed by plate tectonics like an earth mountain. In fact, there's the huge size of these volcanoes indicates there probably isn't much plate activity. The volcano Sapper Mons is about 400 kilometers across and is about 1.5 kilometers high. And if you look at these things, you'll end up with bright lava flows flowing outwards and covering older lava flows. And they tend to be located along fault lines where your magma breaks through the crust. And there's Sapper Mons. It's a twin-peaked volcano. 2 peaks to this volcano, and all of this bright stuff is lava that has flowed down the flanks of the volcano and flowed over the darker, earlier lava, especially here, where you can see the dark and the light. The other things that can be seen are corona. These are circular bulges that can be thousands of kilometers in diameter, and they have a volcanic peak, and then these lava flows and sort of fracture patterns put into them. And these are due to the fact that there's currents of molten lava under the crust, and they flow up and they lift up a dome, and then they pull away, and then the surface below subsides. So where the lava wells up, then the lava falls away, and the surface falls in. And these give you things like pancake domes as well, and pancake domes are circular outpourings of lava. So these kind of features are pretty common on the planet. So these kind of circular features. And if you look on various weird websites, some people try to tell you that these are crashed alien spacecraft and things like that. They're not. These are natural volcanic features. And you can see where they've fallen in. See all this cracking pattern here. Lava channels also exist on Venus. These are channels carved out by lava. These are similar to things called rills that exist on the Moon. These are lava channels existing there. Venus has the longest known channel in the solar system at 6,800 kilometers long and about a couple of kilometers wide. And this is a collapsed area where lava has drained out from beneath the crust and the crust has collapsed. And here it is. Here's some of that channel network that we're seeing. So this is radar data, this is radio data, this was radar bounced off of the surface and detected by the spacecraft, and it's been applied, false color has been applied so you can see contrast between the different surface types. So you can see there's some volcanoes over here and then there's low level material here. So blue means low level and the whitish material is high level, green and yellow will be in between. So that's the surface of Venus. The surface seems a bit more pliable, more like sort of Play-Doh than the Earth's surface. Earth's broken into plates and Venus doesn't seem to look like that and actually has sort of crustal wrinkling and a few fault lines running across it. Places like Ishtar Terra actually have high volcanic plateaus. and about 4 kilometers above the plains. Just giving you an idea of what this planet looks like here. You don't have to memorize any of these things like how much higher Ishtar Terra is than the rest of the planet, but give an idea for the kind of predominant surface features and atmosphere features. But there's wrinkled mountains where crustal motions have formed these things, and this is such a thing. Here's some wrinkled landforms, and this is in Sacagawea Praetera, of course named for the Lewis and Clark expedition. And here's how things are mapped. So we've seen a few results of these things already, but this is a really nice image back from the 1980s probe Magellan. And Magellan basically, or Magellan as some people pronounce it, named after the great explorer. This is Magellan's radio beam penetrating the atmosphere of Venus, hitting the surface and bouncing back to the spacecraft. And this was the first spacecraft that radar mapped Venus's surface. A lot of radar mapping has gone from the Earth since, and from orbit. And here's one of the radar maps. So you can see the planetary radius. This is relative radius. On Earth we use sea level to describe our elevations. Here we don't see that. Since there's no actual sea, you usually use some mean surface level, being this light blue, light to dark blue colour. And there's the same image we saw prior. This came from radar data. There are some interesting flyovers that are available. If you look on the course site, look around the course site and some of the resources, I've given you links to these. And a lot of these you have to be kind of careful because they've, what should we say, exaggerated the Z or Z axis just to give you a bit more relief and to give you a bit more of a spectacular view. But a lot of these images that are simulated from the surface of Venus like this can be a little misleading. Some of these mountains look a little bit higher than they actually would if you were there. But this is an observation of one of the volcanoes from the surface, looking over a ridge. And then we've got some of that wrinkled terrain that we were talking about in Sacagawea Praetera. Of course, the sky is presented as black here. So you would have this against a background of particularly filthy sulfuric acid and carbon dioxide clouds. And this is just a sort of slideshow. Here's some of those lava channels that came back from our radar observations. More coronae and wrinkled terrain. And here's the image we saw prior in a little more of a realistic colour tone. So this is probably the most likely colour of the surface of the planet. So those blues that we were seeing before and greens and whites are really artifacts of the image, just telling you false colours, just telling you the different elevations. This is probably what the planet looks like. And there's maps from all sides, the poles, and from the equator all the way around. So the Venus Express mission, which was an ESA mission, has also gone to Venus and taken a look in the same sense, but it's also looked at the atmosphere and the magnetic field of Venus in a little more detail. That actually says Mars, doesn't it? Whoops. There we go. So this is Venus's North Pole from the Venus Express mission, and this is what we saw in terms of the atmosphere in the visual, and this is what we see in terms of the actual infrared and the heat budget of the atmosphere. And you can kind of see these features are in agreement here, but this is where the energy is and where the heat is going on the planet Venus and its atmosphere. The interior of Venus, very much like the Earth, its density and its size indicates something Earth-like. There's no real strong magnetic field, which is one of Mars Express's main discoveries, and it likely doesn't have a molten core. So the idea of Venus having its rotation reversed due to some molten core is very unlikely. It has a lot of internal heat from some subsurface magma and and that gets vented from the volcanoes, but as far as we know, no molten core as such. But its structure is very similar to the Earth. An outer skin as the crust, some kind of rocky mantle of slightly lower density than the core, and then some core. So it's possible to look at the history of a rocky surface of any body in the solar system, or an icy surface for that matter, by looking at the number of craters that it possesses. When we look at Venus, we don't see a lot of craters. Now we know that every planet in the solar system has been hit by various objects, from its formation and then just by sheer chance. The Earth, Mercury, the Moon, Mars, lots and lots of the satellites of the gas giant planets all show impact features. Jupiter has been seen being hit by several comets at this point in history. So what we've found out is there should be a fair amount of impacts on all of the worlds in the solar system. So if we see a low crater count, if we don't see many craters on the surface of a planet, that means it's a relatively young surface. It's been resurfaced in recent history, and the craters have been filled in. So in terms of geological activity, it's very high. So high geological activity, lots of volcanoes going off, low craters. So the entire crust, the entire outer crust of the planet has been totally reformed in 1 billion years. And a lot of the impacts that we see on other planets are absent in the case of Venus. So it's possible that the old crust, the old surface of Venus, were broken up and sank down, and the lava flows created a new one. So the increased volcanism just caused this widespread surface temperature increase, softened the crust, and gave us a lot of widespread resurfacing. And there are a few craters on Venus, predominantly very large ones that haven't been completely filled up by lava from volcanoes just yet. And if you see these peaks in the center, this says a lot about the surface of the planet. These are probably a little bit of the meteor that hit the planet, and also a sort of blip where solid matter actually acts as a liquid at those kinds of intense energy transfers, and a part of the planet actually sort of flies upwards, a bit like dropping a rock into a pond, where you have a blip of water that goes straight upwards, and this would be that kind of effect. So you often see a lot of craters with these central islands to them. So there have been a lot of Venus probes. Not going to go through each and every one. The most successful of them being the Venera and the various other probes that I've already discussed. Russia has, or the USSR as it was, sent a lot of probes to Venus and were very successful with Venus, and not so successful with Mars. Russia tended to be far more successful at sending probes to Venus. And this is most of those probes that we've been discussing. Obviously there's a fair few failures in here too, but there were various landers and orbital probes, some of them lost. And this list really only goes up to about 2010. And as you can see, Messenger here is listed, the Mercury orbiter. They did 2 Venus flybys in order to get to Mercury. This is a picture of one of the Vega probes that actually went to Mercury, and you can see this in the Smithsonian. I believe it's still housed in the Udvar-Hazy Center part of the Smithsonian, and this is a picture I took myself. And these are very large probes. This is probably a couple of car lengths in size. So we had radar maps that showed us mountains, showed us plains and craters. The Soviet Venera spacecraft actually landed on Venus. And other than Mars, and now a comet, asteroids, and Titan, it's one of the few planets we've actually managed to land a vehicle on. And the rock we found from the results of the spacecraft appears to be basaltic, and the photos actually revealed this sort of dark grey rocky plain and a deep orange glow that was caused by sunlight just making it through the atmosphere. So the Russians, like I said, have more luck with Venus than any other planet. And the Vega series also landed on the planet. So spacecraft in orbit made the radar maps, and then the Magellan probe finished off the mapping, but the Venera probes landed on the surface. And these are the kind of images we got back. So it looks kind of like a cracked parking lot. This thing here is a part of the spacecraft shroud that fell off, and these sort of teeth here are actually part of the outer edge of the spacecraft. This is a test card, so you can see colours. And there's the leg of the spacecraft. You can see this says Venera 14 here. And these are more pictures, very cracked parking lot lookish. And here's some colour pictures. So you can see that orange glow that we were talking about reflecting back off of the spacecraft and the ground. Now, something I actually want to show here is the actual degradation of an image. So here's one image. Here is the next image from this spacecraft. As you can see, the colour has changed and the actual image is poorer in quality. There is a very good reason for this, and the reason is that we were talking about 92 bar atmospheric pressure earlier that this spacecraft was subjected to. This actually crushed the spacecraft, and the Soviet controllers could actually sit and take pictures one by one and look at the degradation of the image and actually saw the spacecraft being crushed very much like a beer can. So that's an example of the kind of temperatures and pressures that we're talking about on this planet. So in its history, Venus and Earth have outgassed about the same amount of CO2, but Venus lacks the water to dissolve the CO2. We've talked about the plate tectonics, we've talked about convection currents and the mountain formation methods. So we've also discussed things like the reason Venus has a young surface, about 1,000 impact craters, more than Earth, less than the Moon. So it says that we're looking at relatively young craters that exist there now with sharp and fresh edges that haven't been weathered yet. So the thick atmosphere might protect it from small meteorites, but the larger meteorites and the lack of very large impact features would suggest that the planet has a relatively young surface. So the surface of Venus is older than the Earth's surface, but younger than the Moon's. So keep predominantly in your head the idea of the very high surface pressure. High surface pressure means high temperature. So about 92 bar, about 450 Celsius surface temperature. If you were to go there as a human, you would actually be crushed by the pressure and boiled by the extreme temperature. And it would be a relatively uncomfortable vacation for everyone involved. So the prospect for life on this planet are probably remote if we're talking about the kind of life that we find here on the Earth.